Okay, welcome to the last lecture. Now, in the previous lecture, we looked at the forces that impact the repulsive and attractive interactions between approaching particles in a colloidal suspension, with the aim of understanding what variables will lead to attraction, so therefore particles sticking together, and what would lead to improving the repulsion and preventing the particles sticking together. In this lecture, we're going to look at pharmaceutical suspensions. Now, most pharmaceutical suspensions are coarse suspensions. And so these are suspensions where the dispersed phase is greater than that of colloidal suspension, so greater than 1,000 nanometers, so 1 micron. Now, a coarse suspension will follow the rules that we've talked about for DLVO theory in terms of the attractive and the repulsive interactions between forces. But there are other factors to consider when a suspension has larger particles, and we're going to talk about those. So this will apply to suspensions, emulsions, foams, and aerosols. In all of these cases, we can have examples where the dispersed phase is greater than 1,000 nanometers, so 1 micron. And the pharmaceutical examples could be for oral delivery, so for instance, children's pharmaceutical suspensions, or topical delivery, so we could have lotions, and we could have emulsions such as zinc cream, or parenteral use, so where you could have the rate of release of the drug depending on the size of the dispersed medium. And this would help to slow or control the release of the drug. So there are a number of examples where we have dispersions of a solid in a liquid, or liquid in a liquid, or other types of dispersions where the dispersed phase may have sizes that are greater than colloidal in terms of the formulation. So as I said, when the dispersed phase size is greater than 1,000 nanometers, so greater than 1 micron, we call these coarse suspensions. And although they do follow the rules that we've talked about in terms of electrokinetic properties, in terms of DLVO theory, they do also undergo sedimentation. And this means that the particles are already big enough, even without any aggregation, to sediment. And sedimentation will obviously lead to destabilization of the colloidal system. Now, we can cope with a certain amount of sedimentation if the sedimentation leads to a sediment that if you shake the bottle, you can easily redisperse it. Then the sedimentation isn't a problem for us in terms of formulation. But if the system leads to a sediment that cakes in such a way that you can't redisperse it, then we have a problem. Sedimentation is governed by a number of things. Obviously, the particle size, as we've mentioned already, if the particle size is large, the sedimentation will be faster. Also, the density of the continuous phase, the density of the vehicle, which we can change by adding additives or other excipients to the formulation, but the density will determine properties of the material that will determine how fast something can sediment and how fast the two phases can separate out. And viscosity of the suspending material, which will determine how fast something will sediment through that system. Now, if your dispersion is stable from the point of view of DLVO theory, then this means that when the particles come together they won't stick together. If they approach each other, they will remain separate. So in our stable formulation, if we have used the DLVO theory to explain the attraction and repulsion interactions between particles, that will all apply. However, even if the particles now are completely separate, they will still be able to sediment if in a coarse formulation, in a coarse suspension, because the particle size is already too big. And therefore they will sediment very slowly, and when they get to the floor, to the bottom of the container, they will have sedimented in such a way that they will cake or clay at the bottom, which means that when you shake the container, they can't separate. So even though these are particles that are stable from the point of DLVO theory, these are dispersions where the particles are not going to come together in solution and stick. Once they've sedimented, they'll form a clay on the surface that cannot be redispersed. So that is a problem. So we have a case here that we need to think of other ways of helping to control the stability. Now, I've spoken about flocculation before. And flocculation is when we have it that the particles, when they come together, they loosely associate with each other. If you remember that that would be a weak attraction between the particles that's followed by a strong repulsion. So they can't get any closer to each other, but they are attracted to each other loosely with continuous phase wrapped around them so that the particles remain discrete. Now, a secondary minima situation, or a formulation where we have quite a defined secondary minima, will be okay for our coarse suspension, because if we have the particles associating with each other loosely, that will create flocks, so lots of these particles associating with each other loosely, that will sediment quite quickly because they're quite large, but will sediment in trapping a lot of continuous phase with them because they are flocculated, so loosely associated with each other. And that means that when you redisperse them, when you shake the system, they do redisperse. Now you can tell if a system is flocculated because if the sediment is very large, is a large volume, then you know that it's mixed with a lot of continuous phase. And so you can see that it's flocculated, and therefore if you shake it, it can redisperse. Whereas if it is formed a cake or a clay, then it will be a very small, a very low volume sedimentation. So you'll be able to tell whether something is flocculated by how big the volume is of the sediment. So the aggregation state of flocculation works quite well for us when we are trying to formulate a system and to get over the problem of the fact that the particles are too large to start with when they're coarse. And so we can create some compromise that allows us to have a formulation that if you shake the system just before you use it, then you've got your dispersion back. So we need to avoid the caked system that I spoke about. So the DLVO theory is useful to us here because it does help us understand how we could create a system where we do have flocculation, where we do have a defined secondary minima. And if our system doesn't have a defined secondary minima because the repulsive interactions are very strong, adding a tiny bit of electrolyte, but not too much, will give us a small minima at the secondary minima points and could create a system that flocculates but doesn't coagulate. And that flocculated system will mean that our particles then trap the solvent when they sediment. We can redisperse them by shaking. So it gets over the problem that we might have if we left our formulation so that the particles didn't interact with each other at all, because now they're coarse they would sediment anyway, and we would get caking. So creating a flocculated system can help us, and we call that controlled flocculation, because we don't want to add too much electrolyte that we reduce the repulsive interaction too much and therefore lead to coagulation, because that's no good. We want to add a little bit of something like an electrolyte just to create a flocculated system. Now, steric stabilization we can also try to use. So depending on the thickness and concentration of our adsorbed layer polymer, we can create attractive forces that lead to flocculation, and because of the polymer that we have on the surface of our particle, the particles don't stick tightly together. So using some of the concepts of steric stabilization and creating the presence of polymers on the surface of our particle can also help to create a system that is flocculated and therefore doesn't that will sediment quite quickly, but doesn't form cakes and doesn't coagulate, which are the two extremes that we don't want in these systems. So if we're going to deliberately add an electrolyte, now we know electrolyte reduces the repulsive interaction between particles, and so for a colloidal system we said that that was bad. Now we're going to add a controlled amount of electrolytes, so we just start to see aggregation form. Okay, and so that will allow us to be able to control the formulation. Now they call the amount that you add that just about starts to form these aggregates critical coagulation concentration, which is a little bit misleading because it really should be critical aggregation concentration, because we're not necessarily creating a coagulated state, we're creating an aggregated state. Okay, so we're adding electrolyte to slightly destabilize our system. And Schultz-Hardy rule mentions this. It says the efficiency of flocculation, which remember is what we're trying to get here, increases with the charge number of the counter ion of the added electrolyte, because it is the counter ion that is going to go to the surface of the particle to form the diffuse layer. So therefore it's the charge of that counter ion that's going to be important, not the co-ion. And this helps us to determine which type of electrolyte would be best for us to add to a system. So what does Schultz-Hardy rule say? It says that added ions of opposite charge to the colloid, or to, in this case, our coarse suspension, act as flocculating agents. And the efficiency of flocculation increases with the charge on the ion. And that also helps us work out what the charge of the particle is as well, which we'll talk about in a moment. But the charge number of the co-ion, so that's the ion that has the same charge as the surface of the particle, has no effect. Okay. So here's some numbers to help explain that. These numbers are they're here to just show you that, how Schultz-Hardy rule works. So there are three different examples. One is a negative sol, so this means the surface of the particle is negative. The second one is the same, the surface of the particle is negative. And the third example, the surface of the particle is positive. Okay, and then we're adding lots of different electrolytes, and we're seeing how much of the electrolyte we need to add in order to cause aggregation of our particles that are suspended in solution. Okay, so this is how much, and it's in millimoles per decimeter cubed, so millimolar. This is how many millimoles of these electrolytes we need to add in order to destabilize our suspension just a little bit. So let's break that down a bit and look at this first one in a little bit more detail. So this first example here, you can see that as that there are different groups of electrolytes that seem to have, you need very different amounts of them in order to lead to some sort of aggregation, to lead to flocculation. In the first examples there, where we have lithium chloride, sodium chloride, those two examples, we have a salt that's made up of lithium or sodium, which is +1, and chloride ion, which is -1. Okay. And if we look at these samples here, you can see that all of these, where the positive ion is +1, you need round about 50 millimolar of this electrolyte in order to lead to flocculation. If we move to these electrolytes here, calcium and magnesium, we then have that the calcium is 2+, the magnesium is 2+, and we have but we have here, you can see examples with different charges of the negative ion. But the fact that the positive ion is both 2+ in this example means that they are all very, very similar. So as you go from the first three to the second three, the charge on the positive ion has gone from 1+ to 2+, and we see roughly a 10-fold difference in the amount of the electrolyte you need to add. And if you go to a 3+ counter ion, in the case of the last three examples, then it 10-fold again change. So you can see that the ion that is changing significantly the concentration of electrolyte that you need to add is the positive ion and the charge number of the positive ion, and not the negative ion, because this is a negative particle. Okay. Let's have a look at the positive particle now at this end. So let's have a look at the positive particle in the same way. And in the positive particle, it will be the negative ion that is affecting. So we can see that in these first examples here, the negative ion is a -1. Okay, and then in the second three examples, the negative ion is -2. And then in this final example here, the negative ion of that electrolyte, of that salt there, is -3. And so you can see that as you go from a negative ion of -1 in the first three examples to -2, we're seeing roughly a 10-fold change in the amount of the electrolyte that's needed to cause flocculation. And again, we're seeing a similar change as you go from a negative ion that's got a charge number of 2 to a negative ion that's got a charge number of 3 in terms of the amount of the electrolyte that's needed. So if you use a electrolyte with a high charge number for the counter ion, so the opposite charge to the charge on the surface of the particle, you will be able to lead to flocculation of your sample using very low concentrations of electrolyte. It's also worth noting that if we didn't know that this was a positive particle, this data would tell us, because it is the negative ion that's having a significant effect on the amount of electrolyte that's needed to be added to cause flocculation, and not the positive ion. Now, the final thing to say about these sorts of systems that you will also cover next year is that we all, as well as thinking about physical stability, we need to also think about things like packaging and information that you might give to a patient. So from the point of view of physical stability, if we can look at things like the sedimentation volume, because our coarse, non-ideal suspensions are likely to sediment over time, and we need to make sure that there's a high degree of flocculation so that they will redisperse on shaking. And this also means that we need to have on the label, and this is required for all suspension formulations that are dispensed, that they must have shake before use on the label. And it's important that the patient is told to shake it before they use it. We also must have a wide-mouthed container with airspace to allow for shaking to have an effect, to mix the system. And changes in temperature, such as freezing or heating or changes in light, could destabilize our formulation. They could destabilize the suspension. And so we need to be careful about the advice in terms of storage and packaging. At the end of the lecture, I want to very briefly talk to you about emulsions. So just for the last 2 or 3 minutes. Now, when we talk about emulsions, we have say an oil phase dispersed in a water phase, or a water phase dispersed in an oil phase. And so that dispersed phase will have similar properties that we have spoken about for suspensions. If the droplets come together and they stick, that's bad because it will destabilize our emulsion. And for the case of emulsion, it's even more of a problem because when they come together, they're likely to coalesce and form one big droplet. And then as those droplets come together, coalesce and become bigger droplets. And that will completely destabilize and mess up the emulsion. Okay. So again, as we said for suspensions, they have kinetic rather than thermodynamic stability. In other words, we need to create the emulsion so that we can keep it stable for a long enough time to be able to use it. And we don't want it to separate into 2 phases and to break. So when you're thinking about emulsions, we have similar concepts. We can get flocculation like you could for a suspension, but now these flocculated droplets are likely to coalesce, and then it'll be even easier for them to break. So we could have it that they separate through creaming, which can occur at different rates. And they can cream at different stages depending on their size. So they could cream as separate dispersed droplets and gradually go to separate out. So the oil would be less dense than water, so it would go up, unless you control the density of your continuous phase. And we can have the same with the flocculated system. That would probably cream faster because they are larger. And then, of course, if you've coalesced and got very big droplets, they will cream even faster, and that will lead to breaking, and the system will be destabilized. So this ideal situation at the bottom here, where all of our small droplets are separate, we'll be able to keep them separate by controlling the density and the viscosity of the continuous phase, and by thinking about the surface properties of these droplets so that when 2 droplets come together, they don't coalesce. We also are not going to want to create systems where we choose to flocculate, because flocculated system is very likely to coalesce. So the rules of emulsions, and you're going to talk about this a lot more in year 2. You can see that emulsions are dispersions. They do follow a lot of the concepts that we've talked about for suspensions, but with added difficulties and differences due to the likelihood that the flocculated droplets will coalesce. And emulsions are used a lot in pharmaceuticals as oil in water emulsions and water in oil. So it depends on which is the continuous phase and which is the dispersed phase. But also multiple emulsion systems. So where you have oil droplets in water droplets, in oil droplets. These can be used to control the rate of release of a drug. They can also be used to administer oil and fats where you need to have those suspended in an aqueous environment for formulation. So there's lots of examples of emulsions in formulation for skin, for oral, and also for intravenous infusion as well. So as I said, we were only going to talk about emulsions for a small amount of time, just to talk to you very quickly about the differences between emulsions and the suspension systems that we focused on in these lectures. In the lectures, we have talked about colloids from 2 points of view. Lyophilic colloids, which is solvent liking. And so the example there is these micelle solutions, because the micelle has dimensions between 1 and 1,000 nanometers. And lyophobic colloids, and also systems that aren't colloidal but are lyophobic because the dispersed phase is bigger than colloidal dimensions. And we call those coarse suspensions. So we looked at solvent-hating systems that were colloidal and that were coarse, where the particles would be bigger. And we mentioned some theories that are very useful for thinking about the stability of these formulations: DLVO theory and Schultz-Hardy rule. Okay, so thank you very much for listening.